Good afternoon, everyone. I'm Jiayuan from Nanjing Tech University in China. Next, I will introduce my study on a simplified field stress model based on node classification for fatigue life prediction. Here is my outline. The first part is the research background. This picture shows the discontinuous components in engineering, like the holes in the high temperature components and the different shape in the pipers. Components with discontinuous are the weak points for fatigue failure. And as we can see, the fatigue factor always happened in this area. To ensure the safe survival for components, standard have been published to guide the survival life. However, the life prediction models used in the engineering is too conservative, like the picture shows. So a lot of models for notched prediction has been presented. And here we give the popular fatigue life prediction of notched components. As you can see, we have divided them into 5 types based on their methodologies, like normal stress approach, local stress strain approach, stress field intensity approach, and so on. However, although they have improved prediction accuracy, but most of them have complex calculated process. Here we select the stress field intensity approach to which have basically meaningful and relatively simple integral equation to discuss and analysis. Here we give the evolution of stress field intensity approach. We have divided them into 3 models, volume integral model, area integral model, and the linear integral model. The stress field intensity considered materials, the max stress at the notch, the stress gradient near the notch, and the stress or strain conditions. The field intensity, sigma Fi, can be seen as the equivalent stress for fatigue life. And the original SFI model using the volume integral for fatigue damage zone. The development of these models tended to be 2 parts, defining the fatigue damage zone and modifying the integral equation. However, there are some questions with these models. One of them is that the same SFI model may predict different materials not bad, not good. So the prediction effectiveness is influenced by the materials. So a suitable life prediction model for engineered systems is required, which may have a unified notch fatigue life 0 and easy to compute and accurate in prediction. And then we give the purpose notch model. Here is the research framework of the modified SFI. We did the elastic and plastic finite element analysis on the notch component to extract stress distribution. And then we used the MATLAB to calculate a gradient for classification. And after simplifying the SFI model, we can do life prediction. The classification and the simplification will show in the next part, and both of them have some connections. Then we give the classification of notch types. After the FEM, we select the most dangerous path to calculate a relative stress gradient, which has, in that case, the tandem stress variation. And then we define the R, which is the stratination point position of the relative stress gradient, and the X, which is the position of the stress that is equal to normal stress. And when the R is greater than X, we define it as the shape notch. And when the R is less than X, we define it as the moderate notch. And when we lock R, and we define it as the observation notch. The example of the notch classification shown in the pictures. And then after the classification, we did some work around the simplified SFI model. Firstly, we select the model which modifies the peak stress, and then we choose the one-dimensional SFI and give the modified SFI model based on the classification of the notch types. As you can see in the picture, different notch types may correspond to different numbers of correct indentation points, which guide the corrected of the equation. And then we can do the life prediction. Specifically, we found a point corresponding to the equivalent stress on the SN cover. The corresponding fatigue life determined an expected fatigue life of the notch component under actual working. That's all about the proposed notch model, and let's make a summary. First, we did the elastic and plastic finite element modeling to for classification of the notch types. And then we did some work around the simplifying the SFI model to calculate the equipment stress. On the another way, we did some work around the smooth specimen fatigue test to get the smooth SN cover. And then we can predict the fatigue life only based on smooth SN cover. The next part is the verification and application of the proposed modes. Firstly is the data collection. We designed four size of notch types and did the high temperature low fatigue test. And then we collect the data from the published literature. In a word, our data including 3 different temperatures, 3 materials with different properties, and 6 size of the notch samples. Here is the results. The notch types shown in the table and the life prediction of the notched specimen shown in the figures. The low cycle life prediction of 316H and GH4169, whereas the notched components is maintained with 2 times error band. Moreover, for high cycle fatigue tests, the prediction accuracy consistent with 3 times error band. And interestingly, we found that for same size of the notch, they correspond to different notch types under different stress conditions. However, they have the wear prediction. And besides, we did some model comparisons. The first figure shows that the predictions obtained using the NSA were conservative, like the blue area in the figure. Although the stress gradient method successfully limited prediction errors to within a factor of 2, it did not successfully predict the lives of all types of nodes. And the second figure shows that the fatigue life predictions for GH4169 notched specimens lying within 2 life factors and most within 1.5 of the scatter band range. The prediction results is better than the 2 other methods cited. What's more, we did some work around the collecting more prediction points through changing the stress levels in FEM. And then we applied the proposed model, combining with the smooth SN cover. We can achieve notched SN cover only based on the smooth SN cover for an engineering risk assessment. So let's make a conclusion. A notch classification method has been processed, and based on the processed notch classification mode and the exciting stress field intensity mode, the relationship between field paths and the notch types has been established. Furthermore, by modifying the peak stress, a simplified field intensity model is proposed. And the last, the equipment stress calculated by this most is a appropriate measure for assessing node stress. Different from peak stress or normal stress, equivalent stress directly reflects the physical quarter of the node stress. And thank you for your attention.